Hello friends, in the last video we have discussed about this damped oscillations, the oscillations which are they get suppressed because of some damping force, okay, and those oscillations they eventually stop, okay. But then there can be, under ideal conditions there can be oscillations, they will keep on happening forever, okay. uh, Practically it won't be possible, but then we can always imagine. There is nothing wrong in imagining things, right? So we have free oscillations, and then we had damped oscillations. Okay, so now here, free oscillations and damped oscillations, let us see what are the differences between the two. Free oscillations, they happen without any external force acting on the body, on the oscillating body. For example, a simple pendulum. Okay, now what is the cause of oscillations of pendulum? Okay, it is only because of the gravitational force of attraction. Okay, is there any other force? No, there is no other force causing the oscillation. Like in oscillations of a spring, okay, the cause of oscillations is the spring, okay, spring force. Okay, is there any other force that we consider? No. Even when the spring is in horizontal position as it, and the mass is placed on some surface, we take it as the surface is frictionless. Okay, so that kind of oscillations you can uh, call those as oscillations as free oscillations or free vibrations. Now damped oscillations, the oscillations, they are happening, but then they are continuously damped by some external force. So they are damped oscillations, and the oscillations and this kind of oscillations, they are going to die out, at some point of time. Okay, and then there is also something called forced oscillations or forced vibrations. Now what are these? The vibrations which take place because of action of some external periodic force. Okay, now for example, you can take oscillations of the piston of an automobile, right? Now what is the force which is causing the oscillation of the piston? Okay, it is the engine force, right? So what happens is, fuel is taken in, then ignition happens, then the fuel and air, that mixture, that blasts, and then that piston is pushed back, correct, and then the crank rotates, crank and connecting on, they have that mechanism. It's a 4-bar mechanism. So basically, because of this periodic suction and ignition and blast of fuel, it so happens that the piston keeps on moving back and forth, correct. So the oscillations of that piston, they are a result of what is happening inside the engine cylinder, correct. So in absence of that force, the piston would not oscillate, correct. Then another example is the motion of a wiper of a car, correct. What happens? It keeps on moving like this, right? It moves like this. Now as soon as you turn off the switch, what happens? The wiper stops. Okay, but then as long as the switch is on, as long as it is getting some electrical energy, it keeps on moving like this, correct. The needle of a sewing machine, as long as that man is pressing the pedal, or as long as he's pressing the switch, okay, and the machine and the motor is on, the needle keeps on oscillating back and forth. Okay, as soon as he stops, the needle stops. Or maybe, if it is an electric sewing machine, and if he is pressing the pedal hard, correct, then the needle would be like this. If he is pressing the needle, that pedal softly, then what happens? The needle will move like this. So the motion of the needle, okay, it will depend solely on what kind of force is being supplied. Okay, so then the frequency of that oscillation, it will depend on the frequency of external periodic force. Greater the frequency of external periodic force, greater would be the frequency of oscillation, correct? So those oscillations which take place as a result of an external periodic force, those oscillations are called forced oscillations. Okay. Now then, there is something very interesting called resonance. Now, what is resonance? Resonance is, um, it has got something to do with the frequency of external periodic force and the natural frequency. Now, frequency of external periodic force is something that you can imagine. Okay, but what about the natural frequency? Now, let us see what is natural frequency. I have this simple pendulum here. Okay, and I just give it some displacement here. I take this bob here, okay, and I'm going to leave it, okay, and then it goes back to the mean position. It goes further and again comes back, and it is set into oscillatory motion. Okay, what is the frequency of oscillation? Okay, now for getting frequency of oscillation, what you need to do is you need to find the period of oscillation. So for that, what would you do? In the lab, when you measure the frequency of oscillation of a pendulum, you will take a stopwatch, okay, and then as you as you release it from here, maybe at the same instant you will turn your stopwatch on, okay, and then maybe it goes from here to here, goes further, comes back here, and comes back to the point from where you released the bob. Okay, you can do that, you can just get that time, but then it would be difficult, believe me. Okay, so what would be the right way of doing it? The right way of doing it would be taking maybe a number of readings, and what I would do is instead of measuring the time for one oscillation, I'll measure the time taken for 20 oscillations or maybe 10 oscillations. Okay, so what I do, I just displace it here and I just release. I release. Now what I'm going to do is I am not going to turn my stopwatch on. Okay. Now when am I going to start it? Okay. So what I do is I just allow it to reach this position, and then at that point I will turn it on. Okay. So from here it comes to here and again here. So that is my one oscillation. So A, O, B, O, A is one oscillation, and like that I will measure the time taken for maybe 10 or 20 oscillations. Okay, so for 20 oscillations, let us suppose it takes about 16 seconds, then 16 upon 20 is the time taken for one oscillation, isn't it? Quite obvious. Now what I'll do, I'll again measure time for 10 or 20 oscillations. Okay, and I'll take maybe 3 or 4 such readings. All the readings will be different. Okay, if I'm very accurate in my measurement, I'm very skillful, okay, then I may get the same reading, but then that is not possible. Generally it is not possible. So alright, so I got some time period of oscillation, and then when I take the reciprocal of time period, that gives me frequency, correct? Now we started from something called resonance. So, and in resonance I had mentioned natural frequency. Now see, this frequency of oscillation, okay, this frequency of oscillation of natural vibrations, I'm considering this as natural vibrations or free vibrations. That frequency is called natural frequency of this pendulum. Okay, likewise, every vibrating body will have some natural frequency. For example, I'm driving my two-wheeler, okay, and there is that mirror, okay, that mirror bar is coming out of the handlebar, okay, and maybe that mirror bar, it might be having some natural frequency, correct? Maybe some part of my bike, okay, maybe the fender on the front side, okay, it might have some natural frequency. If some screw is loose over there, if some screw fitting is loose, then what would happen? It would tend to vibrate. Okay, so it will have certain natural frequency. So natural frequency is the frequency of free vibrations. Okay, now what? Now when the frequency of external periodic force acting on the vibrating body, if it matches with the natural frequency of oscillation or natural frequency of vibration of that body, then what happens? Then the body starts oscillating with maximum amplitude, and then that condition is called resonance. Okay, so now I'll come again. Okay, resonance is the condition in which the frequency of external periodic force matches with the natural frequency of the body. The body starts oscillating with maximum amplitude. Okay, and this condition is called resonance. So now, is it desirable or is it not desirable? That's that's relative. It depends on which condition you are into. Okay, resonance can be useful or resonance can be harmful. Okay, I'll give an example. Soldiers. Okay, soldiers are very disciplined. Okay, so when they march, okay, when they march, they do this, right? Their steps are like left, right, left, right, left, right, left, right. They are very disciplined, not like us. Okay, but now these people, okay, when they're crossing a suspension bridge. This discipline can prove to be harmful, and they're asked to break the steps. Okay, they are told to be indisciplined at times, and what is the reason? Now when they're crossing this suspension bridge, and if they keep doing left right left right left right left right, and if the frequency of their forced vibrations, vibrations caused by their footsteps, okay, if that frequency matches with the natural frequency of the bridge will tend to oscillate with maximum amplitude, and the bridge is likely to collapse, right? That is the reason why they are asked to break steps while crossing the suspension bridge. That is one example. Okay, another example is, maybe you can watch that video of Tacoma Bridge. Okay, how the Tacoma Bridge collapsed. It collapsed because of resonance. Okay, the frequency of external periodic force. Okay, now what is the external periodic force over here? That may be some force caused by the vehicles, passing over the bridge, and there might have been some vibrations. Okay, now even while traveling in a city, suppose you are on a flyover. Okay, you are on a flyover, and imagine that there is a traffic jam on the flyover. You are on top of the flyover. Okay, the side, you are on the left hand side. Okay, and the cars coming from the front, that is the cars on the right hand half of the road, if they are moving normally, then what happens? And you are stopping. Okay, you have stopped at one place, and the traffic on the other side, it is normal. Over there, if you wait for some time, you would find that the bridge vibrates, the flyover, it vibrates, and it's quite frightening. Maybe you experience it sometime. Okay, so this resonance can be harmful, but then any example of this resonance being useful there are. How do we tune in the our favorite channels? Okay, maybe FM radio channels, or then TV channels, correct? Now when you tune in your radio, what you're doing is, the transmitting this radio or FM radio channel, they have some frequency of transmission. Okay, and now your radio, it has got an oscillator circuit. Okay, now your oscillator circuit, it oscillates, and when that frequency of oscillation matches with the frequency of the transmitting radio channel's frequency, okay, then what happens? Then it resonates. Okay, and you hear loud sound over there. So there are various desirable and undesirable examples of resonance. I'll be giving some examples in the on the blog. You can get it in the description. So that was about free vibrations and forced vibrations, then um, damped vibrations. Okay, one more thing, over there we saw that the oscillations are damped, but then at times you need to damp the oscillations. Okay, now can you think of some example of that? Maybe the shock absorbers of a car. Okay, now uh, the roads are not always straight, and they are not always plain. Okay, and if you have some potholes and your car, the wheel enters the pothole, what happens? Okay, it will go down. Okay, and then there will be a jerk, right? So, and then you wouldn't have a comfortable ride, isn't it? So what they do is they have springs. Okay, so the axle, okay, between where we sit, okay, and the axle, there are suspension springs. Okay, so what happens, that bump, it is taken up by the spring, and the spring, it oscillates. Okay, but then again, having that up and down, up and down, up and down motion, that would not be comfortable, correct? So that means that oscillation has to be quickly brought to normal position. So for that you need damping over there. So the springs are damped so that the shock gets absorbed, but at the same time you return to the normal position in shortest possible time. So these are a few things, and in the next video we are going to talk more about maybe some numericals on oscillations, right? Thank you so much.